Alright, so next let's talk about CEM model. And we want to introduce its architecture as well as the pruning layers inside the CEM model. So before we have mentioned the conventional image processing techniques, which may require, some kernel metrics to be defined manually. And based on the kernel metrics as well as convolution operators, we can define different operators for image processing like blow and solve operators, right? As we mentioned before. This conventional image processing requires a manual kernel metrics setup. It may have both advantages as well as disadvantages. So first of all, for the advantages, if we have the manual kernel metrics setup, it may be very straightforward and also very easy to explain the physical meanings of this kernel metrics, right? And at the same time, we can incorporate some expert domain knowledge into the design of this manual kernel metrics as well for the feature extraction as well as for some other operators, right? And in terms of the disadvantages, this kernel metrics setup, with manually, maybe it's flexible and it cannot handle some complex image data we have as well. So because of this reason, we may want to introduce the CEM model as shown in this page. So for the CEM model or the convolutional neural net, this model will learn the kernel metrics from data automatically. It also has some advantages and also disadvantages. The advantage will be, this kind of setup will be more flexible because we have no human being involvement for this kind of, setups, and no domain knowledge will be needed. It will also have some potential problems because this may require lots of data for learning or for training the model because we may have to learn this kernel metrics by the model itself, right? So for the CEM model, these kernels will be learned by the model itself from data. Based on this learned kernel metrics, we can extract more useful features from the input data, right? And for the following task as well. Then we can show you the architecture for the CEM model, and we can explain its architecture in details. In this page, we show you the general architecture for the CEM model. So given the input image data, we want to do the classification of these images into different categories or different classes. Now here we show you with the example with this handwritten numbers. This is an image. Now here we show it as 2, right? We want to identify the numbers inside the image, and it should be classified as 2 as output, right? And based on this input image data, and the size of this image will be 28 times 28 times 1 because this one is a grayscale image. It only requires one single matrix to represent the image, right? And we can see inside the CEM model, we have different layers as shown here. We have these convolution layers, CV1 and CV2. They denote 2 different convolution layers. And we also have some pruning layers. The pruning layers will be introduced in the following pages instead. We have pruning layer 1 and pruning layer 2. Here we adopt this max pruning to extract some useful features from this convolution, this matrix we can get here. And besides these convolution layers and the pruning layers, we also have the FC layers or the fully connecting layers. What is the fully connecting layers? The fully connecting layers is very similar to the MLP we showed before. So they are the layers of neurons with full connection among them. Now here we have the input right from the feature we extract, and it will be the input layer. And the green color denoting the neurons in the hidden layers, right? And the red denoting these output layers. So it will be very similar to the MLP model we showed before. They are fully connected. And also besides these layers, for the layer we have different setups, right? Like we can take the convolution layer 1 as an example. So inside the layer we can have some kernels. And for the kernel we have to specify several parameters. Like the size of the kernel, it will be 5 times 5. The channels, and for the first layer, the number of channels will be N1 channels, right? And also inside we have to specify both the paddings and the stride. Here we mention the valid padding. It means the 0 padding. We don't require any padding at all. Here we assume we are using stride equals to 1. In other words, we are moving the kernels along the images one step at once, right? So here the kernel size is 5 times 5, and given the input image 28 times 28, and with this 5 times 5 kernel, we can represent the output size to be what? According to the formula we showed before, we have the input size n to be 28, and we have the P, denoting the pattern to be 0, and we have the stride to be 1, and we have F to be 5. Then it will be 28 minus 5 plus 1, right? It will be 24 times 24 as the output size. Therefore, given the input image, which is 28 times 28, And with this 5 times 5 kernel, we can represent its output size to be 24 times 24 times N1, because here we have N1 channels for its kernel, for the convolution layer 1, right? Then we can have one pruning layer, which is called max pruning layer. And in the following page, we will show in detail about pruning layers. So here we have a pruning layer, the kernel to be 2 times 2. So in other words, for each of 2 times 2 region inside this kernel, this output, and we will identify the max values inside the region as the output. So with this max pruning layer 1, we can further compress this output into small size output instead. Its size will be 12 times 12 times N1. Because for each 2 times 2 region inside this output, it will be reduced to one single value. Its max value instead, right? And then we can further apply another convolution layer onto it, 5 times 5 again, and then we can further represent a high level convolutional representation of features instead. So with 2 convolution layers, 2 max pruning layers, we can get the representations output. It will be a matrix or high dimensional matrix. Its size will be 4 times 4 times N2. Because this one is still a matrix, right? And if we plan to feed this matrix as the input for the MLP model or the fully connected layers, then we can have to serialize this kind of matrix into a vector as well. So we can flat this kinds of high dimensional matrix into one vector. And we can feed this vector into this fully connection layers and to calculate the hidden layer representation as well as its output. So here we can see we can have one flattening layer as shown here. We flat this matrix into one vector and feed it as the input for the fully connection layer as shown here. Okay, so these are fully connected layers. It will be very similar to the MLP model we mentioned before. You can just refer to this one as MLP as shown here. So inside the fully connected layers, for the hidden layers, we also mention this with dropout. So dropout is actually a mechanism used for avoid overfitting problems. And if you want to try the dropout, you can also search online for more information about it by yourself. And you can also practice to use the dropout layer inside your architecture for the stage 3 as well if you are interested in it. And then based on the hidden layer representation, we can further classify the input image into 10 different classes according to the numbers inside the image, right? Now here it should be a 2, then its output should be the class 2, right, as output. Okay, so this is a convolution layer architecture. We have the input layer, and inside we have multiple convolution layers, and we have pruning layers, as well as fully connected layers. Okay, you may wonder what is a pruning layer we show here. And then we can provide you with more information about prunings we can use in the CEM model. So inside the CEM model, we can use the pruning layers for the information compression. So for example, given one matrix, which is 4 times 4 as shown here, it can be some like a convolution features we can calculate with the convolution layers, right? And then based on it, we're going to further compress the output into small sizes. If so, then we can use this pruning layer to help us. Now here we have this 4 times 4 is matrix output. We can further apply this 2 times 2 filter of 2 times 2 kernels for the prunings with stride equals to 2, for example. If we have such kinds of pruning layer or these pruning kernels with stride equals to 2, in other words, we can shift these kernels on this matrix along both rows and columns. Now we can place this pruning kernel onto the first region first. It's a region, right? Because this one is a max pruning layer. In other words, we can find the largest numbers inside the region as the output. Inside this region, the largest number will be 6. It will be the output for the pruning layer, this 6 here, right? Then we can shift this kernel according to the rows and columns. And if we shift to the right-hand side, because the stride equals to 2, in other words, we can move forwards with 2 steps, moving to this region, right? And we can further find its largest value, it will be 8. And we can move the kernel to downward side with 2 steps, this region and this region, to find the largest numbers, 3 and 4 respectively. In this way, we can compress 4 times 4 matrix into a 2 times 2 matrix instead. And it's a number inside denoting the largest number in each region, defined by the pruning kernels as shown here. So with this pruning layer, we can further compress this output into small sizes to reduce the dimensions and for the following layers, right? So this pruning we can apply to a matrix, and to further interpret its physical meanings, we can also show the illustration, and we'll provide you with the example on the right hand side. Now given an image, for each layer inside the image, we can represent this output as the image, something like this, right? And by applying the pruning to it, what we are doing here actually is to sample some pixels with larger values as the output, right? Now for this image as this layer, by applying the pruning to this layer, we can find its size will be reduced to 1/2, right? However, actually its content is very similar to this image, to the original image, before the downsampling or before the pruning, right? So with this kind of pruning layer, we can compare the size of this image, however, without much information loss actually, because the majority of these pixels with larger values, they are maintained in the output. Okay, so this is pruning and why we have to use a pruning inside CEM model architecture. And you may wonder what the CEM model these layers can learn actually. Inside, we can provide you with some visualizations. The given the CEM model, by the convolution layers and the way the pruning layers, we can extract some features about the input image. In this page, we show you the features we can extract from the input image data, by 2 layers. This is the first layer. Inside, we can find some patterns denoting some edges. We can see, right? This is denoting one edge in this direction. It denotes one edge in this direction. And similar for the other outputs, right? Generally, the first layer of this convolution layer, the output by the CEM model, it denotes some lower level, the patterns of the input images. And then on the right hand side, we show the second layer output of the visualization. So with the high layer, we can detect some high level patterns from the input image data, which are very hard to explain the physical meanings, but from them we can see some hidden patterns, from the image data we input, right? So for the CEM model, it is still something like a black box right now because it is very hard to explain the learning process. But from the output for this layer, we can do some high-level idea or high-level information for this from the input image data instead.